On 56 of Neetcode on 50 valid binary search tree. So the problem is quite simple at the surface. We actually have to say true if it is a valid binary search tree, otherwise we have to return false. Okay, so we can skip this general explanation of what is a binary search tree, and let me just help you uh, getting started. If you don't quite know what is a binary search tree, or if you think you know but you don't really know what a binary search tree is, so a binary search tree is a binary tree where all the value to the right of a particular node are greater, like strictly greater. You cannot have a value equal to it. It has to be greater, and all the values to the left of that node has to be smaller as well, can be equal. All right, so from that 17, I shall not have a value here that is less than 17 or equal to 17. And likewise, on the left side, I can't have a value greater or equal than 17, okay? So I think that this gives you a quite good example. All right, and if I go to that right side, all right, starting from that 35, no value here shall be equal or smaller than 35, and no value here, um, yeah, no value here to the left of that 35 shall be equal or greater than 35. Same thing from that 5 value, no value here to that left side of that 5 shall be greater or equal to 5, and no value to that right of that 5 shall be smaller or equal to 5. And notice that all the values basically here on this branch has to be greater than 5, but they also have to be smaller than 17. Okay, so this is exactly what our algorithm is going to use. We are going to use depth first search, and we are also going to have to keep track of a right bound and a left bound. Okay, so um, let's just define our right bound with this, and let's define our left bound like this with the L. Okay, so, and let's say we start from that 17. Okay, if we go to the right, every single values should be at least greater than 17. So we are initially going to set our left bound to 17. Right bound honestly can be anything at this point, so let's just set it equal to infinity. All right, now that we reach 35, um, we are at a critical point, okay? Because we are going to use recursion, so every single calls will have different right and left values. So at this point, let's say that we decide to go to the left at that 29. Well, we are going to basically set our right value or right bound to that 35, okay? So it is quite limiting in certain aspect because you notice that in that specific branch where the 30 where the 29 is, we only have a range of 18 values that we can have, or 18 integer, right? Or I will say less than that because 17 and 35 are not included. So in this value we actually have to be we have to be there, right? So greater than 17 but smaller than 35. Okay, and on that branch where we average 38, actually it just has to be greater than 35 at this point, because you can have this with basically infinity on it. That will be valid. All right, now let's just see one more example, one more walkthrough with the way we did our previous one, just so you have a good idea of how we are generally going to solve the problem, and then we're going to jump to the code. Okay, so let's now start with our 17, and we go to the left. So every value should now be at least smaller than 17. So we're going to set our right bound to 17, and starting from the left side, well, basically you can have pretty much all the values that are smaller and smaller and smaller. So we are gonna set a left bound to negative infinity. So we are never gonna get something smaller than that. All right. So starting at 5, um, if we go to the left, let's say we decide to go to the left and visit that 2. Well, our right side is no longer gonna be 17. It's gonna be set to 5. All right. So from now on the branch where we average 2, all the values has to be at least smaller than 5, but they have to be greater than negative infinity, which is not a problem at all. Okay, but what if well, I'll let that 5 here. What if we no, in fact, I'll remove that 5. So what if now we have our 17, right, at our right bound. So if we go back to this node 5, um so we undo our previous change, right? So at that 5, all the values have to be at least smaller than 17 and greater than negative infinity. But what if we decide to go to the right where the 16 lies? Where we are going to set our left bound to that 5, okay? Just like this. All right, so now all the values in that branch of 16 has to be, all of them, no exception, greater than 5 and smaller than 17. Okay? All right, I think if you understood that, you get the logic and you at least can understand the code that I'm going to do now. So we are going to use recursion. So to do so, we are going to do, we are going to have our DFS function. So all right, and once we created that, we actually have to pass a couple value in. We first want to pass the node, and we want to pass the left and the right bounds. Okay. All right. I think that if you understood the what I did on the whiteboard from this point, you should get a good idea of how the problem is being solved. So on basically what we're gonna do is that we are gonna use recursion until we reach the bottom of that 3, right? So what I mean by bottom, let's say we define our bottom by that last layer here, right? So we can set all the childs from each single values in that bottom layers have childs set to a value equals to none. And if we actually use recursion and we never return a false along the way, meaning that all the other values above are correctly set for what a correct binary search tree is, it means that we actually have a correct binary search tree. Okay, so if we reach this point, right, which is going to be found by the statement if not node, meaning that it is equal to none, we are going to return 3, okay? And now we are going to recurse back to our, our first call, and we are going to set that true, okay? The cases where we have to return false is if we don't have the following set up. So the following setup is that, or the value of that node, right, is actually not greater than that left bound, and it is not smaller, or pardon me, it is not smaller than that right bound. I think I did an error when I wrote this example in the whiteboard, but hopefully you understood. All right, so what if this value is not greater than the left bound and not smaller than the right bound? Well, this is where we have to return false. All right, and once these two calls are done, we can actually jump ahead in our recursion call, and we have to basically we have to return, right? Um, we don't have to, but what you are going to return is basically the recursion call of the left node and the right branch and the left branch, and both have to return true, right? If no exception. So if the right branch returns false, well, the inferior tree is not a binary search tree. So both have to be set. So both have to be true. So we know we are going to use some and statement somewhere. Okay, so this is then where we are going to call our DFS, and in our DFS we are going to give the node that left. All right. So when we go to the left, we know that the left bound is does not have to be changed, because when we go to the left, we just have to write the new right bound. So in this example, when we go to the 5 from here, well, our left bounds can still be negative infinity. We just have to set a right bound, meaning that this value has to be smaller than that right bound, and that right bound has to be 17. So this is why we are going to use the same left value, but we're going to return that the right bound is the value of that node. Okay, so this is the first statement. This is the first recursion that has to eventually return a true value. All right, And the second recursion call is going to be the same thing for the right branch. So DFS again. This time we return the right side. And when we go to the right side, we have to change our left bound because the right side has to be greater than what used to be there before. So we are going to set that to no that val, but the right side can stay the same, just like this. All right. So there you go. All right. I don't even need um, to add these parentheses, but so let me remove them. So both has to be equal to true if we want to return true. Okay. So we created the entire recursive function called EFS, and now we basically have to return something, right, at the end. What are we going to return? We're going to return the call of this function. So we're going to return DFS. But inside DFS, what do we initially want to give? Well, we want to give the root as the node that we are initially given, and we want to set a right and a left bound that will never be reached. Okay, so we want to have like a statement that says like whatever is inside there, you have to set this as either the right bound or the left bound, depending on which branch you decide to go for. So we're gonna achieve this by saying that the left bound is going to be equal to negative infinity, and the right bound is going to be equal to infinity itself. Okay, so this code should work if I didn't do any typo. Let's test that out. We have a syntax error, invalid syntax. Okay, why is it so? All right, I think I actually have to put them. I apologize for this. I had to keep my brackets on, so let's test that again. Okay, perfect. All right. Cool. So this was a valid binary search tree. I hope you learned in this video, and I hope to see you in the next one.